Hello and welcome everyone. In this video I'm going to explain how the predicted character controller works. I released a video earlier. I don't know when this video comes out or when you're watching this how long ago it will be, but basically in that video I created this predicted character controller from scratch. I explained everything in detail and we tested it and it was working. So in this video what I'm going to do is I'm going to go over the complete script and explain everything and see how things work. Okay? So this is not going to have any kind of testing, like we're not going to build the project, we're not going to run any code, but we're just going to go ahead and read the script and explain how things work again. Okay, so let's get started. Basically, we have a class called predicted character controller, which derives from the network behavior. Network behavior is a class provided by Fish networking, which provides network-related functionality to mono behaviors. Okay. Now we go down here and explain our fields. So we have two private fields which are not exposed in the editor, one called transform and one called character controller. The transform is self-explanatory. It holds a reference to the transform property from the mono behavior. This is usually useful if you want to avoid the native call associated with the transform property itself. So Unity, of course, like I said in the original video, have done some optimizations to this, but I like to do this as a best practice. You might not want to do it, you might do it. It doesn't really matter, it's just a minor thing. Now we have our character controller, which is, well, a reference to the character controller component, which we're going to use. Then we have some very basic variables here, fields here, movement speed, jump speed, gravity scale, and look speed. Pretty self-explanatory. This one is for movement speed, this one is for the jumping speed, this one is how much the gravity affects us. So for example, if we have it set to 9 inside of Unity, this will make it act as if it was 18 in terms of acceleration. And we have our look speed, which is how fast our character turns around. Then we have some input actions. Again, this is pretty much self-explanatory. We have the input action called move action, jump action, and look action. These are the actions which we use to provide inputs for our character, for example, in which direction to move, whether we are pressing or holding down the jump key, and in which direction to rotate or to look. Now down here we have some private fields, which again are not exposed in the editor because they are simply used internally. These are the horizontal input, vertical input, is grounded, jump, and yaw input. Basically, horizontal and vertical input are, horizontal is if we are pressing the A or D keys, so for example, left and right. And then we have the vertical input, which is W or S, or forward and backwards. Then we have is grounded, which is basically whether we are grounded or not. Then we have the jump boolean, which is whether we are pressing, holding down, or whatever, the jump key. And we have the yaw input, which is the amount of rotation applied to the y-axis. Okay, if you hold your hand up in the thumbs up position, your thumb will be sticking up. If you rotate your hand so that your thumb remains in the same position and the palm itself or the knuckle itself rotates, this is called yaw rotation. Okay, then we have velocity, which again is the velocity of our character. How fast is it moving forward, backwards, left and right, and vertically on the y-axis, so how fast is it falling or jumping. Okay, that's pretty much it for the movement related fields and fields in general. Down here we override the onStart network method, which is pretty much a method that's called when the network starts on this object, for this object. So it's called once on the client or the server, but it's only ever called once. Here we assign our transform and we assign our character controller using try-get component, which basically says if we find the character controller, it's okay, but if we don't, log this warning in the console so we know. Then down here we have the time manager property, which we use to subscribe to the onTick event and onPostTick events. These events are basically self-explanatory as well. Tick is called whenever the time manager ticks, as the name implies, and onPostTick is called right after the tick event. So both of these events are automatically invoked by Fish networking. Then we have our two event handler methods, which are just methods we used to subscribe to the time manager. And in onStop network, we unsubscribe from the events we did subscribe to above. Now, down here we have onStartClient, which is a method that's invoked or called on this object when it's initialized on the client. Here, we're going to initialize our inputs, but first we check if we are not the owner. If we are, then we're going to grab the player action map, going to set the movement action, jump action, and look action. Pretty simple stuff, all unrelated to movement or prediction, like directly. But inside our update method here, we check if we are the owners of this object. Basically, if we are the local player, the one controlling this object, okay? We have to read, we have a local variable here called move action value, which stores the result of reading the move action. In this case, it's a vector 2, which represents x and y, or horizontal and vertical input. We get the x property from this vector and assign it to our horizontal input, and vertical input is also assigned the y of the movement action vector. Then we have isGrounded, which is set to character controller that is grounded. You may or may not need this field. I just like to have it to make sure everything is consistent, but you might omit it and just directly use this property. Then we have our jump boolean, which is assigned the value of jump action that is pressed, which is a method provided by the movement action, input action class. Basically, it checks if this action is pressed, as the name implies. So in this case, if we're pressing and holding it, and holding down the jump button, okay. Then we have a look action value, which is a vector 2, as the name implies. It holds the value of the look action, in this case a vector 2. Then we assign our yaw input the x value of the look action vector. This is basically the rotation, or how much the mouse moved on the horizontal or x-axis, okay? So now let's go down here. Just going to collapse these for now because we don't really need them. Okay, let's go to our data structures first, which are used in prediction. So in prediction, you need two classes, one for replication and one for reconciliation. Replication is the process of replicating the player inputs on the server and for other clients. In this case, our movement. So it holds, for example, the horizontal and vertical inputs from the player which did them, and holds the isGrounded, jump, and yaw input values as well. All you need to do is implement the iReplicate interface, have a private field called tick of type uint or unsigned integer, then have a constructor which assigns these fields. Okay, make sure if you don't assign the tick field inside of this constructor that you call the default struct constructor, so it gives it a default value. And then we have three methods down here which are used by fish networking, and you have to implement them. Basically get tick, set tick, and dispose. This one is empty, but it's used internally by fish networking, as this comment implies. And then these ones set and return the tick. Notice that I have the read-only keyword on most of my fields and one of my methods. This is because you should always try to make your value types or structs read-only. In this case, we sadly cannot because fish networking needs to modify some of the properties, but some of these fields like horizontal, vertical, etc. can be made read-only because we're not going to modify them. We're only going to construct the structure and read these values, okay? Same goes for the reconciliation data, which is down here. You need to implement the iReconcile data interface. You need to have the tick, and here we hold the values which need to be reconciled by the server, or what it means is, for example, if the player tries to move to a different position or rotate in an incorrect direction, the server will correct it. And in case there's a discrepancy, for example, due to packet loss, due to latency or something like this, fish networking will use these values to correct the client position on other clients and for the observing player or the owner player as well, or connection, okay? So here we have position, rotation, and velocity, which are the three values we need to correct. Pretty simple stuff. We have, again, like above, like the replication data, we have a constructor, and we have the three methods here, get tick, set tick, and dispose. That's pretty much it for all the prediction structures. So we can go ahead and collapse these now. And let's go ahead and see how they are used. First up here, we have the time manager tick event handler. I know, great method names. But anyway, we check if we are the owners. So if we own this object, we construct a replication data structure and give it these values from our local client, which is a horizontal input, vertical input is grounded, jump, etc. And then we call the replicate method. We're going to go to that, but let's continue explaining this first. If we're not the owners of the object, we run the replicate method or call it with the default value of the replication data. This signals to fish networking that it needs to replicate those using values that it grabs, okay? So this is handled by fish networking. You just have to call it like this, and you don't have to think about it too much, okay? Now, down here inside our replicate method, let's explain it before this one. Basically, we use the inputs to move our character controller, okay? And as you can see here, I have a tick delta, because again, like I said in the original video, if you use time.delta time, things will appear as if they were running in slow motion. For example, if your game is running at 240 frames per second and the tick delta is 60, if you use the time manager, the time.delta time, you will see that, or you will observe that your character is moving at slow motion, because the delta will be very small if the frame rate is 240. But since our tick delta is 60 ticks per second, our tick delta is going to be much higher. So that way, when you move the character around, things will not just be, running at an absolute value or just jumping around, okay? So basically use this instead of time.delta time, okay? Here I have a very basic character controller movement, which I'm going to make a video dedicated to it alone. But basically, we have a local variable called desired velocity, which is equal to transform.right times horizontal input plus transform.forward times data.vertical input. Basically what this does is multiplies the value of horizontal input, which is either -1 or 1 or something in between, by the transform.right, which is the red arrow in the scene view x-axis. And if it's -1, for example, we're going to move to the left, and if it's 1, we're going to move to the right. Why I used transform.right is it's the right of this object right here. For example, if I'm standing in the middle of the scene looking at something, the red arrow will be different from the world red arrow. For example, I might be looking at an angle of 45 degrees. So that way it will return the correct direction, which is in this case right. And same goes for the forward forward vector. If I, for example, looking in a different direction, it will return that forward direction relative to my object, okay? Then I multiply it by the movement speed. Of course, this here will result in our object moving faster if we are holding, if we're moving to the, let's say, diagonally. So if I press W and D or S and D, for example, to counter this and to prevent players from speeding up, there are multiple ways, but the one I like to use is I clamp the magnitude of the desired velocity to the movement speed. So basically clamping the value of the vector, since vector is a direction and the value or magnitude, we clamp that to the movement speed. That way when our character moves, it will never exceed the movement speed. Then, if you remember, we had a field above called velocity. We assign the x and z to the desired velocity x and z. Then we do some checks here in case to jump or not. We say if data.isGrounded. So if we are grounded, I'm going to set the velocity.y to 0. That way we don't sink in case, like for example, we don't try to move down, which can sometimes make it seem like our character is moving in quicksand or moving slowly than he should be. I set it to 0 here, and then I check if data.jump, I set velocity.y to the jump speed. So basically when I'm holding down the jump key and I'm grounded, I will jump. Else, I'm going to increment the velocity.y by physics.gravity times the gravity scale times the tick delta. The reason we add it and not subtract it because physics.gravity by default inside of Unity is set to negative 9.81, which when you add it, it is going to actually subtract it from the y. And then we multiply it by the gravity scale, like I explained above, which controls how much the gravity affects this character. And then I multiply it by the tech delta, so it doesn't increase it by a huge amount, because this is increasing it constantly. This will smooth or spread out the increase over frames. Down here, I just move my character controller and supply the motion parameter as velocity times tick delta, which is going to ensure, again, smooth movement. And for rotation, or for looking around, in this case, I'm just using transform.rotate, vector3.up, and I multiply that by data.yoinput times look speed. Notice that I am surrounding these two floats by parentheses, to avoid creating two vectors, because whenever you multiply a vector by a value, you're going to create one, and then when you multiply it again, it's going to create another. This is something very tiny. It doesn't really affect performance that much, but since it's a simple optimization, why not do it? Okay, so that's pretty much it for replication. Now let's go ahead, and I'm going to collapse this method, and let's explain the onPostTick event handler. And as you can see, it doesn't really need any explanation. It's a very simple method. We call create reconcile, and create reconcile is just as simple. It's simply a method where we create the data used for reconciliation. So we say transform.getPosition and rotation. This is equivalent to using transform.position and transform.rotation, but this is more efficient because it gives us the position and rotation at once, and since we need them both, it's a good idea to use it. Again, simple optimization, why not do it? We create our reconciliation data here, which we create a new one, give the position, rotation, and velocity from our character, and then we call the reconcile method. And as you can imagine, the reconcile method is extremely simple. We just say transform, let's set position and rotation, and then we assign the velocity to the data.velocity. And that's pretty much it for all the logic inside these methods. As you saw, these are very simple methods that we can use to implement prediction in our game, and there is nothing really complicated or inherently difficult about them, okay? So there are some special things we need to account for. These are the parameters that we give to our reconcile and replicate methods. These are special parameters used by fish networking. You will not interact with them directly, meaning you will not supply them except for the data, for example. That's why all of them are optional. What are these parameters, for example? We have the state parameter in the replicate method. This parameter can be used inside this method to, for example, predict future states. For example, to predict whether the character is going to still hold down the jump key, or whether the character is still moving forward, stuff like this, okay? By default, you need to have this parameter set to replicate state.invalid, and then you have the channel, which is something controlled internally by fish networking, basically sending data over reliable or unreliable channels, okay? By default, we set the channel parameter to unreliable. Same thing for the reconcile method, we have the channel only and the data. If any of these parameters, for example, in case of the reconcile method, if you don't have the channel parameter, it's going to throw a compile time error, and you will not able to run your code unless you have this parameter present. Same up here, if you don't have the state parameter and the channel parameters, you will not be able to run your code. And so that's pretty much it for this predicted movement. It is a very simple concept. A lot of people get confused by it because, you know, they hear client-side prediction, correction, reconciliation, replication. But in reality, it is a very simple concept with a very simple implementation, at least in fish networking, which makes it, like, as you can see, very trivial. So yeah, that's pretty much it. I hope you enjoyed this quick recap video or deep dive. If you did, please leave a comment, like the video, and consider subscribing, and I will see you in the next one. Bye-bye.